This video is the first of a series of videos in which I show 6 ways to communicate with the STM32 F103 microprocessor. What will you need for this project? First, you need one of the cheap STM32 103s, less than $2 a piece from a number of vendors. You need an ST-Link V2 programmer, also available for less than $2 from many vendors. First piece of software that you'll need to install is the STM Cube MX. Go to this page here, go all the way to the bottom. You'll click, it'll ask you for your email address, and eventually they'll send you a link where you can actually download the software. Additionally, you will need the STM Cube F1 HAL interface software. So let's run STM Cube. Here we are in STM Cube. Do new project, tell it the processor that we want, type in STM32 F103C8, and finally you end up with only one choice here at the bottom. Click on Start Project, and here we have a layout of the pins of the device. For the purposes of this tutorial, I will do the bare minimum needed to get a blinking light going. So the blinking light on the board is connected to PC13. So here we're going to click and set it to GPIO output. Additionally, you will want to turn on debugging. This is not strictly necessary. Serial wire is the protocol used to communicate with the ST-Link. By default, the board will be initialized to use the internal clock. If you want to use the external clock, enabling you to go up to 72 megahertz, you want to click here on RCC, turn on the crystal oscillator here, then you will need to do some clock configuration. This step is optional. By default, the device will be configured to use the high-speed internal clock directly here in this mux. If we want to use the external clock instead, first we need to turn on the high-speed external clock and then tell the system clock mux to use the PLL output. At this point, we are using 16 megahertz. You can go as high as 72 by clicking here on X9. If you do that, this peripheral clock here will be too high. Easy to solve by simply going here and doing a divide by 2. But again, this step is optional. You can just stay with the internal clock. So that is all of the configuration that is needed on the chip itself. Let's go to some of the project settings. Project settings. Name of your project. I call it Blinky Test, though the code that I will show later will be in Blinky since I already have it implemented. All of the code, when you hit go, will go into this directory here. I prefer to use makefiles instead of IDEs to build my projects. So for that, you click on here and select the makefile. Additionally, we will want to go into Code Generator menu here and click on Copy Only Necessary Library Files. Last, you will need to ensure that you have the hardware abstraction layer firmware installed. STM Cube will look for it here. STM Cube also has the feature of being able to download this for you automatically, but for me it did not work. But if you go to the same link where the STM Cube application lives, you'll also be able to find the firmware there. Okay, once that's complete, and now you'll have a number of files generated in your directory, the most relevant of which will be your main.c. In order to blink a light, you will need to provide some timing. An easy way to do this is to use the systic interrupt handler. So here we will go into the STM32 F1XX IT file, also in your source file, and here we will find the systic handler. This is called every 1 millisecond. It increments the systic counter, as well as calling this IRQ handler, which can be found in the drivers directory, STM32 HAL Cortex. Here's the handler that is called from within the interrupt. It calls this subfunction, which is also defined here, but it's defined weak. So that enables us to override it with an implementation of our own. So going into our main file, I have implemented this callback. This callback is invoked once every millisecond. Now we don't want it to actually blink every millisecond. In this case, I'm having it turn on and turn off once a second. Here we can get access to the current tick counter, which again is incremented every millisecond. And every 1,000 iterations, we either want to turn on the pin or turn off the pin. So that's the extent of the change needed to blink the light. Now let's talk about compilation. In order to compile your code, you will need GCC and related programs. These can be found on the ARM website. You download the version that's appropriate for you. Then you will need to tell your makefile where this is. So going into the makefile, there are 3 changes that I recommend that you make. First, you will need to tell binpath where you've installed GCC. I've done that here. This is all you have to do, but there are 2 additional changes that I recommend. The first of the changes that I recommend is to add the W error flag. This will turn all warnings into errors. I find that it's too easy to ignore important warnings. The second change that I recommend is to change this -G to -G3. This will make available additional debugging information when running GDB. Coming back to our terminal, we simply run make. The main file of interest that's generated here, blinky.elf. Okay, now we have a compiled binary. How do we get it onto the project? For this, I use OpenOCD. OpenOCD knows how to talk to your ST-Link programmer. I have additional information on my blog about how to compile it, as well as how to get it to work. There's a couple of permission issues that you need to resolve. To test that OpenOCD is able to talk to your device, we can run this command here. Again, specifics are on my blog. If you see this output here, then you're in good shape. Now we want to transfer the compiled program onto the device. While it's possible to call OpenOCD directly to transfer the binary to your device, I find that it's more convenient to have this automatically happen every time that I call GDB. To enable this, I've added the following code to a GDB init file. To reuse it for your own project, likely the only thing you'll need to change is this reference to the ELF file as well as this other reference to the ELF file. What will happen is at the beginning, it will reset and halt your device. It will erase everything that's on there now, reset and halt again, and then it gives you control. I find that it's most helpful to put a breakpoint at main and continue. That way, when I get to the GDB prompt, I can immediately put in breakpoints that are relevant to me. Now, in order to run this GDB, I find it's helpful to have an environment variable telling me where GDB is, as it's not the standard GDB that you find on your Unix environment. Also, GDB will need to know where OpenOCD was installed. Having done that, I simply run it, and you'll see here that it has connected to the device, it has erased what was there, it has programmed it, and now given me a debug prompt. If I simply do continue, I will end up with blinking on my device. I hope this tutorial was helpful for you. Please leave comments. Also note that I have other videos talking about 5 additional ways to communicate with the STM32. Hope it was helpful. Bye.